Hello everyone. So today we will see lecture number 13 from the design and analysis of an algorithm. And this is the last topic from unit number first, that is space and time complexity. You know that whenever you write an algorithm or you write a program, space complexity is how much memory your algorithm needs in order to get completed, in order to complete its execution. That's what space complexity is all about. And how much time your algorithm would take or would need in order to get executed completely is called as time complexity. Today we will see the time and space complexity of a linear search. We will start with the basic algorithm, that is a linear search. So this is an algorithm for linear search. You must have done it till now, but let me explain it with the help of an example. Say for example, this is an example where I have 1 2 3 4 5 6 7 8 and 1 2 3 4 5 6 7 8 8 elements, say, in the list of array. And in order to compute the time and space complexity, the first thing which we will see is this time complexity. And for time complexity there are three things which are important, that is, in order to check the best case efficiency, the worst case efficiency, and the average case efficiency. So we will take this example and we will see how can we calculate the best case efficiency of a linear search, what is the worst case efficiency of the linear search, and what is the average case efficiency of the linear search. So by taking this example over here, 5 3 6 7 8 12 and 20. Okay. So let us start with the first element, let us start with the first thing, that is, what is the best case time complexity of a linear search. Okay, say for example, in a linear search, what we have to do is we have to find the or search the element in the list. And say for example, the element you want to search will be represented with k, and the element which you want to search is 5. Okay, and when you run the algorithm, you are seeing that the element which you want to search is the first element of the array. That means you only have to compare the element which you want to search with the list. And how many comparisons you have to perform over here? You will only perform one comparison. When you don't have to compare the whole list in order to search your element, that is called as the best case. So we can say the best case time efficiency, because in this case we get it first, so we can say the best case efficiency for this particular list in order to find the element 5 is big O of 1, because you only have to perform one comparison, and here this 5 is n. And if we have to generalize it, so we can say the best case time efficiency on n input list of a linear search is big O of 1. Okay, easy. Now, the second thing is the worst case. There are two situations for the worst case. One, if the element is present in the list. Element is present in the list, and element is not present in the list. And in the worst case of linear search will be when the element is present, but is present at the end. If the element is present but is present at the end, that means you have to perform n comparisons, isn't it? Say the element which you want to search is 20. How many comparisons you have to perform? You have to perform all the n comparisons in order to reach the element. And in the second case, if the element is not present in the list, still you are going to search. Say for example, the element 21 you want to search and 21 is not in the list, still you have to perform all the n comparisons over here. So we can say the worst case time efficiency of linear search in both the cases on n input size will be equal to big O of n. It is big O of n in both the cases if the element is present in the list but is present at the end of the list, and if the element is not present in the list at all. In both cases, its worst case time complexity is big O of n. Third, average case time complexity. In average case time complexity, there again are two possibilities for it. One possibility is element is present somewhere in between, and element is not present, right? Again, in average case, if the element is not present, obviously it would be big O of n. If the element is present, but element would be somewhere in between the list, and list can be so long. It is not necessary in the list you would be having 5 elements or 10 elements. In your list you can have 5,000 elements, like that. So how we do that? If the element is present in the list, we call that as there is a probability of successful search, and let that be equal to P for successful search. That means if the element is present. And for the unsuccessful search, that means the element is not present in the list, let that be equal to minus P minus 1 for unsuccessful search. So now consider that element we are searching is found at position I in the given list. Then the probability will be equal to P divided by N, isn't it? So the average case time complexity of linear search on n input size will be 1 into P by N plus 2 into P by N and so on, plus I into P by N plus into N into P by N plus N into 1 minus P. The first part is when the element is present, that means for the successful search, and the second part will be for the unsuccessful search. So over here you can see that P by N is a common term, so we have already done this in the previous lecture. So 1 plus 2 plus 3 and so on, plus I plus into N plus N into 1 minus Pn. This is nothing but the summation of first n natural numbers, so we can write it like this: P by N is N into N plus 1 divided by 2 plus N into 1 minus P. So here this N and N can get cancelled out. This will be P into N plus 1 divided by 2 and plus N into 1 minus P divided by 2. So this term is for the successful search, and this is when the element is not present in the list. Now we will take two cases for both. The first case is like if the element is present in the list, then we have to substitute in this as P equal to 1. P equal to 1 means for a successful search, that means the element is present in the list. So substitute this, so P into N plus 1 divided by 2 plus N into 1 minus P. So 1 into N plus 1 divided by 2 plus into 1 minus 1. So this will get cancelled out. So we can say if the element is present in the list, where P belongs, the element is present in the list, its time complexity is N plus 1 divided by 2. And if you will substitute P equal to 0 for unsuccessful search in the same, though the first term will be equal to 0, and 0 into N plus 1 divided by 2 plus N into 1 minus 0, so this will be equal to big O of N. And about the space complexity, as this is the time complexity in 3 cases. If we will see or look at the algorithm, For the whole operation, we don't need any extra variable in order to solve this problem, in order to execute this problem. Here we only take the list numbers and we take a single variable. It is not going to change. When you take constant variables which are not going to change for the whole execution of program, here your n can be 5, still you would use the same variables. If you will increase your n from 5 to 5000, still your variables would remain same, the space would remain same, you are not going to change it. So for that purpose, the space complexity of linear search is big O of 1, because it would remain constant all the time. Thank you, have a nice day.